So we're in this chapter on exergy. We've covered a lot of material. We're down here. We really need to get into the exergetic, or what we call the second law efficiency. Sometimes I'll say the second law efficiency. Sometimes I'll say the exergetic efficiency of the turbine, compressor, heat exchanger, whatever. They're used synonymous. Okay, so as a review, we had exergy as a property for a closed system. We also had Exergy balance equation for a closed system. This is a key equation. You can read that equation. You can say, oh, the Exergy of the system goes up or down depending on if I have some transfer of Exergy during the process, in with the heat, out with the work. But what we have right here is we have this funny term which is subtracting the non-useful pushing back the boundary term, because Exergy is a useful work, not just work pushing back the boundary. So this term's a little annoying at times, but basically we want to take the total work, subtract off the non-useful, and what's left is the useful part of the work that the boundary, that the system does. And then we also have the ability to destroy Exergy because of irreversibilities. Sometimes you write that as EDEST, Exergy destruction rate, and one of the easiest ways to calculate it is it's the dead state temperature times the entropy generation during the process. That's all good. Then we had a new property, the flow Exergy. I didn't rewrite it here. It's pretty straightforward. And then we used that flow Exergy for open systems, where we did an Exergy balance on a control volume where we had mass flow across the boundary of our system. Here we only do steady state, only do one inlet, one outlet. And this is the equation used 99% of the time. So you have a very similar term as right up here. A little less complicated because we took out the integral such that that boundary temperature stays constant as the heat is transferred across it. So you could have written this as an integral, just like this is written as integral, but if TB is constant, it simplifies it. Okay. And this is the Exergy transfer with the heat, sometimes written EQ. This is our Exergy transfer with the work. Maybe we put a rate on there because it's the rate at which it's being accomplished. That's a power. And then we had our mass flow rate, bringing in Exergy, taking out flow Exergy, so inlet, exit. And then we also had an Exergy destruction rate. That Exergy destruction rate could be written as T naught times sigma dot. So we get equations for properties, equations for Exergy balances. And we use them to solve a lot of problems. Well, last time we started in on this exergetic efficiency, or the second law. Let's continue there. So here is a turbine. Last time we talked about having mass flow stream through the turbine. And the purpose of that turbine is to extract some energy out of the fluid flow stream to produce shaft power. So this inlet flow Exergy is not the same as the exit flow Exergy. Actually, the exit flow Exergy needs to be lower than the inlet flow Exergy. Otherwise, there's no chance of making power. Okay, so you write that Exergy balance equation. I know we could start with the 0 equal to, hey, is there any heat transfer? We could have that Exergy transfer with the heat. For this problem, it's no heat transfer. That's our standard assumption on a turbine. So guess what that term is in our Exergy balance equation? 0. We also have minus W dot. That's this power coming out. And so if I have 10 kilowatts of mechanical shaft power coming out of that turbine, I have 10 kilowatts, the same magnitude, of Exergy flow in that shaft power. It's a 1-to-1. 1 kilowatt of mechanical power is 1 kilowatt of Exergy transfer. The heat transfer wasn't. It had that term. Let's go back and look at it. This is always less than 100%. The coefficient here is just 1. Okay. And then we brought in the fluid flow Exergy took out some fluid flow exergy, and that's really what comes out of that mass flow stream. And then we had the destruction of exergy. We can rewrite that equation so it's a little more easy to read. We say what comes out of the fluid flow stream, EF1 minus EF2, is equal to, it goes into the shaft power out, or is destroyed. And we want as much of this, a large fraction of that, to go to here. But if this is 100% on the left-hand side, then this could be 90% 10%, or 80% 20%, or whatever, 60% 40%. Well, we don't like a lot of exergy destruction, and right away you see, well, there's the definition of an exergetic efficiency. The exergetic efficiency is they use the epsilon, and if I'm talking about a turbine, I like to add that subscript T to my exergetic efficiency, but the book doesn't always do that. So you have to pay attention. Sometimes they put a subscript, sometimes not. That's equal to what it's coming, the mass flow rate times EF1 minus EF2. It's all coming out of the fluid flow stream, and it's either going to where I want it to go or it's being destroyed. And we want to see what fraction, what percent goes to where I want it to go. W down. There it is. That gives us a ratio that's 100% at the maximum. You want it as high as possible, close to 100%. Well, this is the way the book writes it. But it's the same equation, isn't it? See that? All right. You ready to pick up on the problem we left off last time? So, we had this problem here. We had a steam turbine. It was well insulated. We had the pressure, the temperature, the mass flow rate, exit pressure, and it had an isentropic efficiency specified, little review of Thermo 1. And we then solved for the power out of the turbine and found out it was around 2,501 kilowatts. We then solved for part B, what's that entropy production rate in the turbine? That's sigma dot. That's 3.22 kilowatts per Kelvin. And then the exergy destruction rate in the turbine, E dot D, comes in at 959 kilowatts. So this was W dot equal to 2501 kilowatts. The last part, what is the exergetic efficiency of the turbine? So the exergetic efficiency of the turbine, the answer we're going to get is 72%, but just write that exergy balance equation. So what is the in and what are the two outs? The in is with the mass flow. What's out? Shaft. And what's my other out? Destroyed. Just wasted. Wasted ability. Not energy is wasted. The energy is always conserved, but it's the wasted part of that energy that could have been used to produce useful work. That's what's been lost or destroyed. Okay, so this is my mass flow rate, EF1 minus EF2. This is equal to the shaft. You know what? That was 2501 kilowatts, wasn't it? And what was it destroyed? 959 kilowatts, wasn't it? So what is the rate of exergy flow out of the fluid stream? The sum of those two. You add that up for me. Tell me what you get. And then once you add that up, give me the exergetic efficiency. Show me that it's 72.3%. I'm going to pause and walk around. So how many people got that the flow was, 3460 kilowatts? And then the efficiency, the exergetic efficiency is, well, this is what we got. We wanted to make that number larger, but that's what we've got. And we provided to the device the flow rate of 3460 kilowatts, so that exergetic efficiency comes in at 72.3%. Now let's talk about the compressor pump. If you understood the turbine work producing device, it's the same for a compressor pump. What do we have here though? We have a fluid stream. Let's do this. let's talk about the relative magnitudes of EF1 versus EF2. It's a compressor or a pump. For a turbine, the outlet EF2 is lower. What about a compressor or pump? EF2, is that going to be smaller, lower than EF1, or greater? It'll be greater. So what you're doing, I know the book shows this as a positive W dot out. Hence, they're going to have a negative sign in their final equation for the exergetic efficiency. So I'm going to try to be consistent with the textbook. But it's very difficult for me because that negative sign I want to get rid of it. I want to flip this around and show the power in because I know it's in to a compressor or a pump. That's my nature. I want to show it in. But I'm going to try and be consistent with the textbook. So you write an Exergy balance equation. This time, we're going to write it like this. I'm going to put negative W dot. That's my in because of the shaft power. Where does it go? It goes into two places that are the outs on the Exergy balance. It can go to the mass flow rate times the EF2 minus EF1, increasing the fluid stream's exergy, or it can go to waste, being destroyed due to irreversibilities. Now, maybe I did this equation a little too fast. Maybe what you need to do is go back and start with this equation every time. I know Professor Creamy loves that. Right? Go back to the fundamentals. Show me. Why is that term crossed out? Oh, every time. Q dot is equal to 0 for my compressor or pump. And then I play with these and manipulate, and that's the equation I get. Make sense? Okay, maybe you take 3 steps to get there, but we need to get here. But I think it's readable. All right, and then we have the exergetic efficiency for my compressor or pump. Well, we wanted as much to go into increasing the flow stream's exergy, the fluid stream's exergy, and it costs power to drive the compressor pump. Are these equations consistent? Yeah, I think so. True? Yeah, all right. The pump is very similar to a compressor. You ready to solve a problem? Okay. Nitrogen N2 at 2 bar and 250 Kelvin. You know, I could spend a lot of time just talking about words to the problem. Because right away, when you see a problem like this coming out of Thermo 1, you see nitrogen N2. What goes off in your brain? What are you thinking right away? Forget about the steam table. Forget about the refrigerant tables. It's an ideal gas, and yes, we have some tables for ideal gases. All right, that's perfect. This is at 2 bar and 250 Kelvin. Let's talk about the pressure. What's the pressure of the air in this room in bar? About 1 bar. What about the temperature of the air in this room? 300 Kelvin. So it's a little higher pressure, 2 bar, double the pressure, and it's cold. It's 250 Kelvin going into the compressor. It enters a well-insulated compressor. Well, we're going to find that it's probably not beneficial to insulate compressors. If you ever are around mechanical equipment, people insulate turbines, but they usually don't insulate compressors. But that's another topic, not for now. But when you see well-insulated compressor, what do you know about Q dot? 0. And that's why they put an insulated compressor, so it's easy to analyze. And if you do have some heat transfer, often it's away from the compressor unless you have a really cold inlet to the compressor. And that heat transfer away from the compressor helps you during compression of an ideal gas. Okay, let's keep reading. It exits at 22 bar. Does that seem reasonable? It jumped from 2 bar to 22 bar. Yeah, that's what a compressor does. Boosts the pressure. How about the temperature? 550 Kelvin. Oh, you can't trick me, Professor. This is a device with no heat transfer. Q dot's equal to 0. If it came in at 250 Kelvin, it has to go out at 250 Kelvin. We have an error in this problem, don't we? You didn't fall for that Thermo 1 trap. No way. It does come out at a spanking hot 550 Kelvin. No heat transfer? Come on, I don't believe it. The only way the temperature can go up is if I have a heat transfer. True or false? False. When you have an ideal gas, all you have to do is compress it. You compress it with no heat transfer, that temperature is going up. See how much you mastered in Thermo 1? See, isn't that great? All right, we continue on. It has a mass flow rate of 0.2 kilograms per second. We assume the ideal gas model. Even if they didn't tell you, you could justify it. You go back and calculate that compressibility factor Z for both inlet and outlet, find that it's very close to 1. It's justifiable. But this saves us some time. We're just going to treat it as if it's an ideal gas. Always an ideal gas everywhere through our system. Great. And you ignore the effects of motion. What are they telling you there? Ignore the changes in kinetic energy. And ignore the effects of gravity. They ignore changes in potential energy. Let the dead state temperature and dead state pressure be given. Start the problem first. Calculate the isentropic compressor efficiency, and the answer is 81%. Now there's a part B and a part C, but I busted it. Let's just do part A first. We don't need the dead state information for part A. How are we going to get the isentropic compressor efficiency? Yeah, you make a lot of sketches. Maybe you'd make a sketch like this. I'm going to show W dot going into the compressor. I don't want to deal with a negative W dot. And this is going to be a T1 and a P1. And this will be a T2 and a P2. Over here, we know that information. You start organizing all the information given to us in a problem, right? And then we probably want to go with a property diagram. Oh, there's a lot of property diagrams that we've been exposed to and mastered. We could go with the PV diagram. Probably not the favorite one for this problem, because we're interested in isentropic compressor efficiency. We could go with the pressure enthalpy. No, we're going to emphasize that property diagram later, more in this semester. But what property diagram probably is very helpful? Temperature, entropy. And right away, the students, oh, I've seen temperature entropy diagrams, and they throw out this big thing. Okay, what's that called? The dome. Okay, do we have nitrogen anywhere near the dome? It behaves as an ideal gas. But don't all substances have a dome? Yeah, they do. So guess what? Tuck that little dome way down there. Out of the way. That's where it is. You want to get cryogenic temperatures and all that? You got it. We'll zoom in down there later. But not for this problem. We're out in the ideal gas region. Okay? So, out of the way, or even leave it off, dome not needed. Okay. So, this is one of those hard things. On a temperature entropy diagram, if you had a process that started maybe state 1 here, and they said, oh, it's a constant temperature process, it would either go like this or like that. All right. Let's do this. Start the process here. If it was a constant entropy process, it could go like this or like that. So those we have down pretty easy. But, oh boy, we have to recall for an ideal gas, what does a line of constant pressure look like? What does it look like if I had a constant pressure process, and right there is a line of constant pressure? That line of constant pressure is the 2-bar line. Excuse me. And then, if I had another line of constant pressure for an ideal gas, it would be up like this, 22 bar. How do you know that? I passed Thermo 1. I don't know what else to say, but you got to be familiar with how these property diagrams are and why they work. So we start with this entropy and this temperature. Hey, it started at 250 Kelvin, did it not? On a line of 2 bar. It ends up somewhere on the line of 22 bar. If I had an isentropic efficiency of 100%, where would state 2 be in relationship to state 1? Straight up. Yeah. So this is the line to the state 2, S. That's as if it was isentropically compressed. But we didn't get state 2S given to us in the problem. And they're going to ask us to calculate this isentropic efficiency to be 81.3%. So where is state 2 actual? And if you want to be real precise, you draw the line from 1 to 2S as a solid line, and 1 to 2 actual as a dashed line. Okay. Long discussion on why we use the dashed line, but let's leave it alone for now. Let's come over here. What is our temperature on the actual exit of that compressor? 550 Kelvin. So, if I need to calculate this isentropic compressor efficiency, how am I going to do it? We go back and review what is our isentropic compressor equation. It's a ratio of two powers, if you like, or two specific energies, or ratios of enthalpies. There's a lot of ways to work it. But it would be something like, my actual work into the compressor compared to the minimum work into the compressor to achieve the same pressure change. The compressor really isn't to beat it up and make it hot. The compressor is just to boost the pressure. That's the goal. I need to get it up to 22 bar. So what you do is you review the definition of the isentropic compressor efficiency, and it turns out to be the ratio of this. If I could have done it isentropically, achieving the same pressure change, that would have been my minimum work in. Or my actual work is larger, so I'll put the minimum over the larger, and there's my definition of isentropic efficiency. Somebody says, okay, isn't that related to the enthalpy in and the enthalpy exit? Yeah, that's right. Which enthalpy is greater for the compressor? Is the exit enthalpy greater than the inlet enthalpy or less? Which enthalpy is larger for the compressor? This is the outlet of the compressor. Exit enthalpy is larger, isn't it? Yeah, energy is going in by the shaft to drive the compressor, and it's boosting the pressure and the temperature of the outlet stream, hence the enthalpy going out is a lot higher. So this ratio, you can write it as H2 minus H1. After my earlier lecture, somebody came up to me, I don't understand where you got that equation from. Energy balance around that compressor. The energy going in, if it's adiabatic, it's Q dot's equal to 0, remember? It's steady state operation. You're just boosting the enthalpy. Okay? All right. So let's continue on. Let's put this S over here. This is going to be H what minus H what? 2S. H2S. So what do you mean by H2S? Well, can you tell that this is the temperature 2 actual, this is the temperature 2 isentropic? Which one's lower? The 2S. It's a lower temperature, as if it could have been done isentropically, reversibly, and it would have a lower enthalpy, because remember, for gases, what is the enthalpy is a function only of temperature for an ideal gas. So sometimes they'll write it like this: C sub P times T2S minus T1 divided by C sub P times T2 minus T1. T2 actual if I want to put an extra subscript on there. There's assumption going from this one to this one. What's the assumption? Constant specific heats. You don't need to use that assumption. Let's not use that assumption. This would be assume constant specific heats. But let's work with the tables. And we're going to need table A23, which accounts for variable specific heat. Variable specific heat meaning temperature dependent specific heats. Okay, so if I look at this equation, I want you to go into that table A23. So we're not going to use this approximation, although a lot of problems will say assume constant specific heats, and that's the route you would take. But here we're going to stop right there. Can you go into the table and get H1? We need that in this equation. What is H1 equal to in the table? 7266. And we're good engineers, so we're going to put our units down. What are the units on that H? Kilojoules per the kilomole. And if I look at this equation, I have one little typo or syntax error. What's my error that I need to fix? It's on a per unit mole basis. Now, everybody likes to work with the per unit mass basis. True? But you can also use a per unit mole basis. True? So what would be the difference if I came through and I just put a bar on each one of these terms? That's fine, isn't it? So we're going to put everything on a per unit mole basis. So here we have the H1s in that equation. Okay? I'm going to need either this H or that H next. I'm going to get all four H's. Well, there's only 3 unique values. But which one do you think is a little easier to get? H2 actual or H2 isentropic? Which one's going to be easiest to get next? H2A actual. In the table, can you look and find H2A actual? 16,064 kilojoules per kilomole. You see that? How did you get that again? They told us the exit temperature. The exit temperature is 550. H2 isentropic. I'm going to pause, walk around and see if you can't at least describe in an equation. How are you going to get H2S? All right, well, let me pick it up here. That's why we like this diagram, because what do we know about the process from 1 to 2S? What's constant during that process? Almost too obvious, isn't it? S is constant. And then you say, well, how does S change for an ideal gas as pressure and temperature change during the process? Go and review. There's nothing embarrassing about needing to review something in the previous chapter. Section 6.5. That section 6.5 is entitled Entropy Changes for an Ideal Gas, something like that. How do I calculate the change in S for an ideal gas? And then there's equations in that section, 620, I believe, version A and then version B. One is on a mass basis, one's on a molar basis. And so it says S2 minus S1 is equal to S naught at T1 minus, T2, minus S naught at T1 minus R natural log of P2 over P1. Or sometimes they'll write it like this. They'll write S at T2 P2 minus S at T1 P1. Meaning the entropy is a function, is affected by T1 and T2. The change in entropy is a function of the temperatures as well as the pressures. Okay, this was like version A, and then version B. What's the difference between version A and version B? It's like S bar 2 minus S bar 1 is equal to S bar naught at T2 minus S bar naught at T1 minus R bar natural log of P2 over P1. Professor, I think I see that all you did was, put bars over top of things. So maybe we should put a bar over that temperature. No. Well, why not? You put a bar over the H's, you put bars over U's, you put bars over S's, but then you never put a bar over T. Why? I don't have time. Let's press forward. But it doesn't make any sense. The temperature is not on a per unit mass or per unit mole basis. How about the pressure? Should I put P bar? No, same thing. Those are different type of properties. They're intensive simply by nature, not dependent on the mass. Okay, now let's take a look at this equation. I forgot. What is R bar? Does anybody remember the numeric value? It starts off with 3.14. No. 8.314. You had it right. I was given pi to fool you, right? 3.14. No, 8.314. The units. Kilojoules per kilomole Kelvin. You don't have to memorize everything, but hopefully when you become familiar with it, it helps you recall and leads you to the solution. All right. Hey, what's this R versus this R bar? Are they the same? Nope. What's the key moving back and forth? Molar mass. What's the molar mass of nitrogen? 28.01, and that's somewhere in our tables, in appendices. All right? Just like R bar. You don't have to memorize it, but you should know what it is and how to find it. So what we can do is, this equation we want to use. So for this problem, this side is equal to 0 when you go from state 1 to state 2s. It's isentropic. And then you're looking at S naught of T2 minus S naught. Oh, I forgot. Hey, what do these naughts mean in this S? Why don't they put T naught and 2? And why don't they put P naught 2? What does that naught mean on that S? Okay, it's for one good way to remember it is that it's for atmospheric pressure or nominal pressure. It's not for, it doesn't account for changes in pressure. It only accounts for changes in temperature. S naught's only a function of temperature. So when you go back and look at it, some integral, the CP's with the T's, right, dt. But this is where the effect of the change in pressure is isolated in my equation for the change in entropy. Pressure changes do affect the entropy change of an ideal gas. Temperature does also, but it's nice that the pressure effects are confined over in these terms and the temperature effects are confined in those terms, and those terms are based on 1 atm pressure. That's how they calculate it. All right. Okay. Standard reference pressure. Okay, so using this, what you can do is you say this is T2S that I'm trying to calculate. I know the starting temperature. I know the final pressure. I know R bar. Guess what? I look up S naught bar. No, I'm sorry. I calculate S naught bar. True? Somebody did this correctly. Isn't that who showed me their number? Isn't that what you did? Intermediate step is you calculated S bar naught. What was that equal to? S bar naught, this is of T2S, is equal to T1 plus R bar natural log of P2 over P1. And when you calculate that, forget, let me look it up here. It comes in at 206.306. That's way too many digits, but hey, keep them. Then you went in and you interpolated in table A23, knowing that's S bar naught, and you interpolate to find H bar at T2S, and that interpolation gives us the 14,420.4 kilojoules per kilomole. If you wanted to, you could also get T2S. It's that same fraction of interpolation in our table, and that temperature comes in at 494.6 Kelvin. So right at 495 Kelvin. This is all a good review of Thermo 1, is it not? But I'll tell you what, if you don't have a mastery of Thermo 1, well, get it because you're going to need it. Okay? All right. All right, so then I finally get this H bars. We come up to this equation. We calculate the compressor isentropic efficiency. Let's go ahead and put in some numbers. 14,420 minus, what was my H1? 7,266. 7.66 divided by 16,064 minus 7,266, and you get the efficiency of 81.3%. Nothing to do with Thermo 2. Everything to do with Thermo 1. Let's press forward. Ready? So we calculated that. Now, what is my exergetic compressor efficiency? And numerically, it's not the same. It's close in value, but it's not the same. How am I going to calculate that exergetic efficiency? You could put the EF exit minus EF inlet divided by W dot divided by M dot. If you like the minus sign the textbook uses, fine. Isn't this the right form? Okay. Just working, let's leave the EF1 or EF2 minus EF1 there. What about that denominator? We already used that. That's a difference in enthalpies, isn't it? Isn't that my H2 minus my H1? Isn't that from the first one? We basically used that already. Somebody says, oh, you didn't put the bars on this. Hey, guess what? We can put the bars on it all. Now it's on a per molar basis, no problem. And we just got these out of our tables. It's just I need to basically get EF1 and EF2. Well, let's work with it a little further. Is that H2 minus H1 minus T naught S2 minus S1? Bar, 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 bar. And then we divide by H2 bar minus H1 bar. Let me ask this question. Are these changes in H's the same as these changes in H's? Yeah, sure are. And actually, you can start to see kind of the repetition in it. It's like, you know, this is my exergy destruction. I can see that. This is my work supplied. This is then what went into the fluid, because it's a difference of what was supplied minus the destroyed, and this is what was supplied. Anyway, let's press forward because we need to be able to numerically evaluate it. So I got these values done. I've got my dead state temperature. Notice it's 25 degrees C, right? Should we add 273 or should we add 273.15? I think I talked about it already. Just add the 15 and let the computer handle it. Your calculator handle it, okay? When in doubt, throw in the extra digit. Even though this temperature is only given to 2 significant digits. You're basically adding one that's 5 significant digits. So the answer is still 2 significant digits of accuracy. But let's press forward. How am I going to get this S2 and S1? That equation 620b, true? So that one we go back, it's very similar. 2 minus S bar 1. What is the common mistake? The students will do this and they'll stop. I'll grade exams after exam. This will be where they stop writing that equation. But where does the equation end? So this was evaluated at the temperature 550 Kelvin, and this was evaluated at the temperature of 250 Kelvin. And you can then calculate this exergetic efficiency, and it's 89.3%. All right. Are you with me? Thumbs up if you're with me. Thumbs like sideways or something like this if you're going to just have to review this on your own, because maybe you're lost a little bit. Okay, that's honesty. That's honesty. Good. No shame in that. That's why I'm going a little slow. If some students are sitting there going, oh, I'm so bored. Patience. I want everybody to pass. All right? Not just the elite. So let's press forward. Part C. This is maybe a little more doable. What is my rate of exergy is destroyed in the compressor? If you solve for part A and B, the pieces of the puzzle are already there for us. True? So we want to calculate this E dot D in units of kilowatts. Okay, how am I going to calculate that rate of exergy destruction? Let me pause and walk around, and if I get a few people to write down the right equation, then I'll press forward. How are you going to calculate that rate of exergy destruction in that pump? So hopefully a lot of us have it, but you have to do something like this. You have to have T naught times sigma dot, and then you say, okay, well, what's sigma dot? After the second law, you're going to find it's related to the mass flow rate, and then S out minus S in, isn't it? Okay, well then, hey, guess what? This is T naught times N dot times S bar 2 minus S bar 1, because, hey, we've been working on a molar basis. So what is the M dot? Well, that's a mass flow rate. What is the N dot? Molar flow rate. How do I move back and forth between them? Use the molar mass. Yeah, the molar mass. And so what was our molar mass? 28.01 on the nitrogen, true? What are the units on this molar mass? Kilograms per kilomole. And so you just use that all the time. So if I have M dot and I want to get that into make N dot, do I divide by the molar mass or do I multiply by the molar mass? Yeah. How many times on exams will I see a student where they should have divided, they multiply? Too many. Avoid those errors, please. Okay? So you can get the molar mass, and then we already know how to do this, don't we? We did it. This is that S2 naught bar minus S1 naught bar minus R bar, natural log of P2 over P1 to calculate the actual change in entropy from the actual initial to the actual final state. Just N dot T naught. Okay. That help? Let's press forward then. Well, we have heat exchangers, and you can come up with a second law or exergetic efficiency for a heat exchanger. So we have a hot stream, and should we color code this, red, and then a cold stream, blue. And something flows out of the hot and into the cold, energy. But it also, a part of the energy which is available to do useful work also flows out of the hot into the cold, and that's how we get the exergetic second law efficiency. So here you can start with the general balance. What flows in? Mass flow rate of the hot, EF1, and then also the mass flow rate of the cold times EF3. This is an inlet, this is an inlet. Equal to the mass flow rate of the hot, EF2, that's an outflow, minus plus M dot of the cold, EF4, that's an outflow, and that's an out, plus you could have the destruction of exergy. How is it destroyed? Anytime you have heat transfer through a finite temperature difference, you have entropy generation, you have exergy destruction. Let me rearrange it like this. M dot hot, EF1 minus EF2. That's what comes out of the hot fluid stream. Mass flow rate cold, EF4 minus EF3. That's what goes into the cold fluid stream or is destroyed. And so then our exergetic efficiency is what we desire, a lot that gets into the cold fluid stream, divided by where it comes from. It all comes out of the hot fluid stream. There it is. That's our second law of efficiency for a heat exchanger. Without mixing. There's no mixing on this heat exchanger. Guess what the next heat exchanger is going to be? With mixing. Okay. You ready for the next one then? So here is our hot fluid stream. Here is our cold fluid stream. What comes out? Our warm fluid stream. And the same idea. Something flows out of the hot and into the cold or is destroyed. So we have the mass flow rate of the, well, first of all, I should do mass balance. If you do a mass balance, the M dot 1 in plus the m dot 2 in is equal to the mass flow rate 3 out. That's going to be used. So what we have is m dot 1, which is our hot fluid stream, times, it comes in with a high flow exergy, leaves with a flow exergy of state 3, and the cold fluid stream, m dot 2, it comes in, well actually it's going to go out with a higher flow exergy. EF3 is greater than EF2, or the exergy is destroyed. Where does this equation come from? Exergy balance. And so our exergetic efficiency is we want as much of it to go there, we want very little to go there, but that's can't be avoided. So we have the exergetic efficiency is m dot 2 EF3 minus EF2 divided by m dot 1 EF1 minus EF3. We don't have time for this problem, so what I'm going to do is I'm going to pause, stop, and I'm going to hand out the exam and spend the next 15 minutes talking about our take-home exam.